All right, y'all. Let's get started. Okay. So a couple brief announcements. First of all, I wasn't able to find a reading that I liked for this particular week. I do have a couple readings that are great for when we're considering more complicated variations of these models. So, like I said, you will get some reading for this unit. Sorry, I couldn't find anything that quite works for this early part, but insofar as you use the readings, and I hope many of you do, there will be some for, I think, next week will be the start of them. In addition, I'd like to do these course evaluations. I haven't sent out the link for the course evaluation yet, but you can expect it either later this afternoon or tomorrow. As always, this really helps me a lot, and I do read all of the evaluations, and the reason I do that little analysis of the evaluations every time is to show you that, hey, I'm actually paying attention. So it really does help me a lot, and in particular for the past month or so, there have been some brand new units that I've never taught before, never taught data management before, I've never taught philosophy of science before. I thought that they were useful, but I mean, you're you, and you have something that I don't. So that in particular, I really appreciate some feedback on. I'd like to know if that content was useful, and I'd have to be curious about some feedback on it. So not required, but it'll help me a lot if you do take the course evaluation. All right, we're continuing on with repeated measures designs where you have one person, business, whatever, that has multiple measures, maybe at different points in time. I'm going to pick up with the example that I started Monday with, but I'm going to give you another way of thinking about that same process that we went through back on Monday. So this maybe will give you another conceptual anchor point to maybe understand what it is that we did. So like I said, we're working with the same data set. We have 50 people evaluating grants, and each person both evaluated a grant that was low quality and a grant that was high quality. So this is what that data set looks like. Remember, we've got multiple rows with the same participant ID, indicating that the same person reviewed multiple grants, gave multiple observations. And the process that we went through on Monday was we considered each of these chunks of multiple rows that belong to one person, and we sort of thought about doing a little mini regression on each of those mini data sets. So you do 50 different regressions where you predict the score that the reviewers gave from the quality of the grants. And for each of those 50 chunks, each of those 50 little mini data sets, you get an intercept and a slope, where the intercept, you can think of that as the average of the two scores. The slope you can think of as the difference between the two scores. That gives you sort of a second data set that's compressed, that has 50 rows with a bunch of intercepts and slopes, one intercept and slope per participant. And for doing statistical testing, you can sort of think of testing the average of each of these columns against zero. So that's the process that we went through on Monday. Another process that we could have followed looks a little bit like the following. So You might remember how from our data management unit, there are multiple ways of structuring the same data set. This way of structuring the data set is a tidy version. But we can structure this a little bit differently so that it's untidy, but still may be useful for insight. So what I'm going to do is use this function spread. What spread does, as a reminder, is it takes variables that are embedded in a single column. So say the quality dichotomous column, you could take that column and bring up that minus 0.5 and positive 0.5 into the column headers, into the column names. So what I'm telling spread to do right here is I'm telling it to take this should be quality dichotomous, but you got the idea, take that column and the numbers that are going to go below the new columns are found in the baseline column. And this is what happens if you run that command. So one thing that I'll direct your attention to, we have these two new columns, one called minus 0.5 and the other called positive 0.5. I can rename those just for illustration. And this 6 and 3 are the same 6 and 3 that used to be spread out, or that used to be rather longer. So what I've created is a new data set that instead of 100 columns, or 100 rows, excuse me, 2 rows per review. I've now got a wider data set. This is sometimes called wide format. That is also shorter, it has fewer rows. Instead of 100 rows, it now has 50 rows, just 1 row per review. Yeah.
Can you do that if it has more than 2, like you have negative 0.5 and 5, or you have like negative 0.5 and 0.5, which is 3%?
It'll work the same way. Yep. So the question was, what happens if you have multiple values that occur in quality dichotomous? So instead of minus 0.5 and positive 0.5, minus 0.5, 0, and positive 0.5, it worked just the same way. So we'd end up with 3 rows, 1 per value that occurs in that column. Spread is a very useful function. It makes kind of tricky restructuring problems where you're trying to get from one data set format to another a lot simpler. Although I have to admit, I have to look up the help file for spread almost every time I use it. So it takes a little bit of practice to understand what you're doing, and I still look it up every time I use it. I find it a little bit unintuitive. Nevertheless, though, it's quite useful.
So your key equals, is that the variable that you're spreading across?
Key is the variable that tells me the new columns that I'm going to have. So key tells me, spread is going to look into the key column and say, aha, there's a minus 0.5 and a positive 0.5. Those are going to be the new names of my restructured columns.
Do they need to be consistent then?
If it's not consistent, so one thing that could happen, for example, let's say that reviewer 5 not turn in one of their reviews. Let's say we have an NA here instead of a 3. Actually, what spread will do is it will just move that NA into the appropriate place in the column. If we just don't have this row, it'll also generate an NA. So spread is smart about how it inserts the index. So I suppose actually the answer is it doesn't necessarily need to be consistent, although it might do things that you don't expect if there are inconsistencies with the original data set. Questions?
What you're saying if NA is found, that makes it into the column?
So let's say that there was an NA in the bottom right corner here, where that 3 is. That NA will go here.
What if it's in the quality?
Oh, if you have an NA in the quality column, it'll make a new column called with the name NA. And if that's the only NA, then that column will have a bunch of NAs below. So like I said, it can do unexpected things if there's not due by your data set. So make sure it's worth checking that beforehand to make sure that it's probably going to do what you think it's going to do. Other questions? I'm going to focus on this restructured data set because we can use this restructured data set to accomplish the same kind of analysis that we did on Monday. So let's just, for the sake of argument, say that I want to create some new columns to the right of plus minus 0.5 and positive 0.5. One of them is going to be the average of each of these two values, and one of them is going to be the difference of these two values. So this is what the average column looks like. You might notice that we're getting the same numbers in this column as we have in this one, the one that we made kind of implicitly when we were doing this little mini regressions, one per viewer. Likewise, with the difference column, that gives me the slopes that you would get if you did those little mini regressions. Does this kind of make sense why this is happening? I mean, when we worked with regressions originally, when we worked with like a simple t-test, a dichotomous predictor, we found out that you can think of the intercept as being like a grand average and the slope as being a mean difference. Well, we're seeing that same idea just applied to two values. So one way of thinking about what we're doing when we did these mini regressions, at least in this one example, is that we're taking averages and differences. We can then take this wide data set, this restructured data set, and test each of these columns, each of these created variables against 0. So literally what we're doing is we're taking an average of two variables and a difference between two variables, and then just fitting a one parameter model on each of those created variables. And intercept only one. Everybody follow this? And this approach is equivalent to the approach that we took on Monday, where we just used that one function called Elmer, that new function. In this particular case, we'll get the same results. So this is the output that we got from Elmer. Gives you a lot of stuff. The main place that you're going to be looking is under the fixed effects, at least for now. And remember, if you're using Elmer, you have to use this other new function called capital A ANOVA in the car package to get your p-values. Here I'm just showing you some code that restructures a long data set with multiple rows per viewer. So I'm calling the long data set D_L for D_long. Right here, I'm just renaming the or I'm changing the minus 0.5 and positive 0.5 to low and high, so that my new columns are doing something nice instead of minus 0.5 and positive 0.5. Here I'm using spread, which I showed you on the previous slides, and I'm creating these averages and differences. Then you fit two one parameter models. One that I'm calling m_average, and one that I'm calling m_diff for difference. So here are the results from M underscore average. This is that one parameter model that I'm fitting on the average values for each discipline, for each reviewer. And in this average model, we see this familiar parameter estimate, 3.05, or 3.04, excuse me. Along with the same F value and P value that we got from Elmer. Does someone want to take a guess? What does this 3.04 represent in the context of rate reviews?
The average period,
The average across.
like on all reviewers.
The average across low quality grades across all reviewers. Yeah, so this is the average score averaged across quality that a given reviewer gave to their grades. If we look at the second model, M underscore diff, we see this minus 0.72, which we saw here as the coefficient for quality underscore dichotomous. If we were to take a guess, what do you think that minus 0.72 means in the context of grade reviews? Little reminder here, these 1 to 9 scores are a bit unusual in that 1 is actually the best score.
Did the average change between quality scores between low and high quality grades?
Yeah, it's the average difference that a given reviewer had in their evaluations of the low and high quality grades. There's one difference in the interpretation of this coefficient here that we haven't seen before, in that this minus 0.72 refers to the difference that one reviewer had between their low and high quality ratings. So instead of being, we have a group of people who gave one set of grade scores and a group of people who gave another set of grade scores, this minus 0.72 refers to a difference within one individual reviewer. So that reviewer gave one grant a better score and one grant a worse score.
So if you were to write that, you would say, what's the difference for one reviewer?
It's the average difference that a given reviewer had between their evaluations of low versus high quality grades. So this hopefully provides another lens to understand what we're doing with these mini regressions. One way of understanding it is that we're literally calculating quantities for each reviewer. We're calculating one number that represents something that might be interesting about what reviewers did. And then we're doing a second analysis that sort of aggregates across the reviewers for a given quantity. Like, what's the average difference that reviewers have between their high and low quality evaluations? Yeah.
I'm a little confused on this last intercept. So is it not the difference between the averages of the high and low ratings?
Yeah, in this particular case, it would be. But it's a little bit better to think of it a little bit closer to the context of the problem, to think of it as the average difference that one reviewer had in their evaluations. I think it's closer to the context of the problem because each reviewer had multiple grades, and what you're interested in is how the reviewer's behavior changed when they graded each grade. So you could think of this as the difference in the mean for the high quality grants and the low quality grants. I think it's a little bit more precise to think of it as the average difference in how the reviewer reviewers rate each grade. Is that helpful?
Yeah, it just seems a little semantic in this case.
Yeah, it is. It is. I think it's, again, it's slightly closer to what happened in the context of the problem. If you think of it as like, how did one reviewer's behavior change across grades or across conditions or whatever? But yeah, you're right. It's a little bit semantic, and it doesn't matter that much, especially in this particular example.
Not sure if you went over it already, but what's up with that control function at the top?
Yeah. So I mentioned this a little bit on Monday, and you'll learn more about this on drill. But Elmer has this thing called an optimizer, which is necessary for fitting a lot of these, at least the more complex versions of these models. Here it doesn't matter so much, but you do still need to tell the optimizer certain things in order to get it to fit this particular model. Elmer is more, I think it's nice for understanding how these models work. It is necessary for more complex models, which we will get into. But it'll be plain if you don't do that first line where you say control, and you give it some information about what to do with the model.
So we always have to do that before.
For these early models, yes. Yes. Actually, for these simple models, I find it a little bit more convenient to calculate these different scores. That's usually how I approach analyzing this kind of data. But you'll see that the basic Elmer syntax that we're using here generalizes in a really nice way that I think helps understanding to much more complex models. Glad you asked that. Other questions? Okay, so with this information in mind, we can sort of formalize the process of analyzing repeated measures data a bit more. I'm still not going to tell you all of the guts of linear mixed effects models, which is the framework that we're using for this data. And that's because it is a little bit complex, and I think it makes sense to think about the different components and stages. So we're going to get a little bit more formal. We're still not quite all the way there. Not quite all the way to where we're going to end up. So, like I said at the beginning of this lecture and on Monday, you can think about analyzing repeated measures data as sort of fitting little miniature models, little miniature regressions across different subsets of the data. So you have one subset per reviewer or per unit that has repeated measures. I'm just going to give the intercepts and slopes that you get from those little miniature regressions a little symbol to make them a bit easier to write out as I'm formalizing this bit of the linear mixed effects model. So the intercepts that you get from these miniature regressions I'm going to call base of 0, and the slopes I'm going to call base of 1. So 0 is, when we extended the general linear model, 0 was often the intercept, was always the intercept. 1 was the first coefficient. So I'm just using that same standard here. So for this particular example, this really simple example where we have each person reviewing 2 gradients of their inequality, you can think of these little miniature regressions as fitting this model up here. So for a given participant, you can predict their score or or making predictions about their score using one intercept, which is an average, and a slope times quality. So this is very much like when we first start building out the general linear model. We start from an intercept-only model. This is just slightly more complicated where we have both the intercepts and slope. Everybody following this so far? This is just that little miniature regression I was talking about. We're fitting this 50 times, one each for each review. Once you do that, you have some derived quantities, the means and differences that we were talking about in the second data set. And on the second data set, you have a second stage where you fit intercept-only models for each of the derived quantities that you have. You have one intercept-only model for the reviewer intercepts and one intercept-only model for the reviewer slopes. So this is going to give you a grand average, an average reviewer intercept and an average reviewer slope. And another important point about this second stage is that each of these grand averages has their own error. So this column right here has, not everybody gave the same grand average score across the two grades. There's going to be some variability in how harsh the general or lenient the reviewers were. Likewise here, there's going to be, across each reviewer, reviewers are going to vary in how different they gave the high quality and low quality grades, or how different those scores were across the high quality and low quality grades. Reviewers are going to vary in their sensitivity to that quality manipulation. And that's this error term here. So the fact that I've given these two error terms different subscripts just indicates that they're different quantities. So the error in the intercepts is not going to be the same as the error in the slopes. Kind of makes sense because if you think about fitting two intercept-only models across two different variables, well, there's nothing that says that the error for variable 1 has to be the same as the error for variable 2. It's exactly what we're doing here. How we do it? So this whole process, you can think of as proceeding in two stages. In the first stage, you break apart the data set into different subsets. Each subset is defined by, a reviewer or a school or whatever your units of interest happen to be. Often there'll be participants. Often you'll be doing repeated measures with a participant that gives you multiple scores. You then fit these little miniature linear models on each of those subsets. And from those little miniature linear models, you'll get a bunch of intercepts and a bunch of slopes. So this first stage involves fitting these little unit level linear models, a bunch of them, and then getting some derived quantities from those little linear models. In the second stage, you fit some overall models on each of those derived quantities. So an overall model for the intercepts and an overall model for each of the slopes. So the fact that this proceeds in two stages might give us some insight into why Elmer, this new function that we learned about on Monday, has its syntax set up the way it does. This part in parentheses off to the right is the model that we're fitting for that first stage of analysis. So we're telling Omer for each unit defined by participant ID, each participant ID represents one review level. I want you to get a slope for quality underscore dichotomous, and by default, it also gives you an intercept, just like by default, this part will give you an intercept here. For the second part, this is the second stage of analysis. So it's saying, okay, once you have all those derived quantities, I want you to fit a model with an intercept and a slope for quality dichotomous. So we'll take the average of all the intercepts, and then we'll also take the average of all the slopes.
And we're working with the data set with 50 rows.
Yes. Well, that's what's happening under the hood. When we fit this model, we're going to use the long data set, but what we're telling it to do is create a smaller data set with units defined by participant ID. This first stage, where you have these like little miniature linear models, that's often called the random effects portion of the model. I've mentioned that term in passing on Monday. The random effects are basically the things that can vary from participant to participant. Each participant is going to have a slightly different intercept. Each participant is going to have a slightly different difference between time and quality rates. The reason they're called random effects is a little bit technical. And that's because we're assuming that these the participant intercepts and slopes have some sort of distribution, just like our overall error term does in a regular linear model. So we have multiple error terms. That's that point that I was making about how the intercepts are going to vary a bit, and that level of variability is going to be different from the variation in the slopes. So that's one difference, one big difference between this kind of model and the models that we usually work with, and that suddenly we have multiple error terms. That's a big idea that I'll come back to more as this unit continues. Right now, just bear in mind, we've got multiple error terms. The fixed effects are called fixed effects because they're assumed to be the same for all participants. So we're assuming that there's a common rand average of the average value that people give to these reviewers, even though there's people departed it from this rand average. We're also assuming that there's some rand average of the average difference between high and low quality rates. If you're a little bit fuzzy on why they're called that, I guess you could just remember that the random effects are the things that can be different across people. Each person has their own individual average of the scores that they gave to the kids. And the fixed effects are that's like your overall free error estimate. That's like the average that you get of those individual intercepts and slopes. How we doing? So this is a slightly more formal version of, or gives you a slightly more formal structure to understand what we're doing. We're going through this two-stage process. In the first stage, we have these models that can give results that can be different for each reviewer. And in the second stage, we do some analysis on those derived values. That's a good way a good heuristic way of understanding what it is that we're doing. So next I'm going to show you how to use this like general framework to make, to do some slight tweaks to the models that you fit. And I'm going to start relatively simple. I'm just going to add one extra variable. So we're still working with the same data set, the same, actually exactly the same underlying data, but I'm going to add one extra variable, and that is the sex of the reviewers who gave these reviews. So some of the reviewers in this data set are men, some are women, and I've coded this variable minus a half and positive half. So our data set looks like this. We're still working with this long data set where we have multiple rows for each reviewer. I just added an extra column called participant underscore sex. That is consists of minus a half and positive half. So one thing that I want you to notice is that if I look at the rows that belong to a given reviewer, they can only have either minus a half or positive half across those two rows. So the sex of the reviewer does not change across the course of the study. It's the same for all rows that the reviewer gives us for the study. That's a bit different from the row that for the quality manipulation. So actually by design in the study, quality is different for the two rows that belong to a given reviewer. So it looks like that the sex variable is somewhat different in kind from the quality variable. The sex variable does not change across the course of the study, whereas the quality variable does. The reason this matters is that variables that do not vary with across rows of a given unit. So if you're dealing with some characteristic of reviewers that's fixed across the course of the study, that cannot go into that first stage of analysis that I talked about, where you're getting those little individual linear models, one for each review. So if you think about it, like if I try to use something that doesn't change within reviewers, I'm not going to get a meaningful slope. That's going to give me technically an intercept. I can't get the slope for something that does not change within the unit. Does that make sense? Quality is different though. The fact that quality changes for a given reviewer, for all reviewers, means that this is something that can go into that first stage of analysis, where I'm fitting these little individual linear models. So the key concept here to understand is that there are some variables that do vary within units, within reviewers in this case. And there are some that don't. And those two different kinds of variables are handled differently in a linear-based effects model.
Gotcha.
Yeah.
So whenever you're allocating these to good reviews and bad reviews, how can that be a random effect? How can that effect be found?
Well, let's see if I can understand what I think is your question. And please ask a follow-up if I don't answer. The terminology of random effect is a little bit confusing. The meaning of the term random here just means that this is something that we're assuming can be different across reviewers. It's this a second type of error term. So we're used to working with one error term. That's the difference between what we predicted and what we actually got. You can think of these random effects as the difference between that grand average, that average, say, intercept for all reviewers, and the intercept that they actually have. Does that answer your question?
Yeah.
So when we've worked with error terms before, we've had, say, a regression line that's like this, and what we've considered an error is the difference between an individual point and that regression line. Here, the meaning of what an error is slightly different, and the way it's different is that we have, say, a bunch of slopes, one per reviewer, the slope being the quality effect. And an error curve here is by how much a given reviewer's slope differs from the overall slope. So is that clear? So the meaning of an error is it's the difference between these derived quantities, these things that we get from these little miniature regressions, one per reviewer, and the overall quantity, the average across all the reviewers.
Okay, so this quality variable here, because it changes across levels, that introduces variance in the slope for each participant.
Correct.
Correct. So the difference between that, or the possible difference between that slope and the overall slope, is the error in this case.
The thing that's in the error is the difference between an individual reviewer slope and the overall average slope across all the reviewers.
So it's the actual difference.
Correct.
Not the potential possible.
Yes, correct. So again, the reason that we can calculate a within reviewer slope for quality is that for each reviewer, we've got a point here and a point here. So we might have, that might be reviewer 1, this might be reviewer 2, and so on. But if we're considering sex, if we take a look at reviewer 1, they have 0.5 each time. So maybe there's a point here and a point here. There's no way to calculate a slope between these 2 points. We just get a vertical line. Does that make sense? So we're thinking about this new model where we have participant sets. At that first stage of analysis where we're fitting these little miniature regressions, one per reviewer, our little miniature regression model is the same as it was when we did not have participant sets. that's because participants X can't contribute to these miniature regressions. We get that problem where we're considering one reviewer, they have the same X across all their scores. So this part of our model is the same. So we go through that process of getting an intercept and slope, 50 intercepts, 50 slopes, one per reviewer. And we've got this new data set that contains the intercepts and slopes. We also have participants X. So participants X did not contribute to this first stage of analysis, but it can contribute to this next stage. So let me ask you first about the overall model for the intercepts. What do you think the overall model looks like for the intercepts? So last time when we did not have participants X, we just looked at, we just did an intercept-only model on these derived quantities. What do you think we're going to do now that we have an additional variable, participants X? Yeah, specifically, what do you think the model's going to do? You can talk in terms of the formula syntax. Okay.
Interactive model?
Interaction between what and what?
Interaction between scores given across six.
Well, so let's consider this intercept column first. So we're going to fit a model for the intercepts. Before, when we did not have participants X, the model that we fit just had one call intercept, and that's it. Now we have an additional column. So what do you think the model is going to look like now that we do have participants X?
Just have two intercepts, right?
Well, we'll have two parameters. One of them is going to be the same as we had before. So intercept equals U0. Then what else is going to go into this model? Yeah, so we'll also have coefficient for sets and an error term. We've got an additional variable. It can contribute to this intercept model, where we're using intercepts as the outcome variable. So we just add. That's it. Okay, so let's think about the slopes. This is this other derived value that we got from our individual participant models. What do you think the model is going to look like for these slopes? Well, so let's think about where we were before. When we did not have participants X, the model was slope equals an intercept plus an error term. So what changes now that we have an additional term?
Same thing.
It's the same thing. So we have another slope for participants X plus an error term. These models actually look very, very similar to the old ones. It's just that we have an additional variable that doesn't contribute to this first stage, but it can contribute to the second stage. So you just add it as the additional predictor at that second stage. That is to say that we can change around what these models are, just as we could with any other model that was worked with. We add in extra predictors, we estimate parameters that are best in some sense, given those predictors. And we get results. So we're just adding one additional predictor here, which is this one sex. But you can imagine that we can tweak this model in lots of different ways at the second stage, just as we have any other model. Questions on that?
What's the other question of this example? Is it, scores differ across men and women?
There are several questions. I'm going to get to interpretation on the next slide, but you can ask, for example, does the overall average score that reviewers gave to the grants vary across men and women? Is there a difference in that overall score? Or another question that you could ask is, does the difference in quality does the difference in scores that the reviewers gave to high and low quality grants differ for men versus women? So one is a question about averages, the other is a question about differences. Let me get to the next slide and please tell me if it still isn't clear. So first of all, we're extracting all of these like intercepts and slopes across all of the reviews. So I showed you this this image on Monday. The thing I want you to see is how, just as before, on this first stage of analysis, each reviewer has their own intercept, that horizontal gray line, and they have their own slope, which is the difference between these 2 points. And that horizontal gray line and the difference between these 2 points is different for each reviewer. That's that first stage of analysis. So I guess it's a little bit further, but I am getting to interpretation. So please ask again once we're there, if things still aren't clear. So once I've gathered together all of these intercepts for each reviewer, we've got a grand average of the slopes, and we've got some variability across that or around that grand average. But some of these reviewers are men, and some of these reviewers are women. So just like when I first talked about adding information to these graphs, you can color code the information points one color versus another to add that extra information. Well, I can do that with the reviewer intercepts. So it's a little hard to see here, but you might see that the intercepts down here tend to be yellow, whereas the intercepts further up tend to be green. So it looks like there's a difference in the intercepts for male reviewers versus female reviewers. And just like I did with other kinds of models, I can draw 2 separate lines on this graph. One that represents the average intercept for women, and one that represents the average intercept for men. So what I'm I'm doing here, what I'm allowing to happen is I'm allowing the average score that a given reviewer gives to their grants to vary across males versus females. I'm looking at the gender difference or the sex difference in those average scores. Does that help a little bit with what's happening conceptually? So here's the figure that I showed you that represents what's happening with the slopes. So I've got a grade average for the slopes, representing the average difference in scores across high and low quality grades. And I've got some variability in that difference. Some reviewers are really sensitive to the difference in quality, so they have a really steep slope, and some are less sensitive. They have the slope towards zero, and there were a few that gave a better rating to the low quality grade. Just as I did with the intercepts, I can color code these individual slopes according to whether the slope came from a male reviewer or a female reviewer. So in this graph, it's not necessarily clear whether there's a difference in the average slopes for males versus females. It's a little bit hard to see, but there are a few more yellow lines in the upward direction. And just as I have with other kinds of models, I can now draw an overall average for the female slope and the male slope. So this is one way of thinking about it is that's literally the average of those differences for female reviewers. Those average of those differences for male reviewers. And this is what you get. This is a combination of information about intercepts and slopes. It's a little bit busy, which is why I started with the previous graphs. But right here is the line that represents our average intercept and our average slope. These gray horizontal lines are the differences from the intercepts, and these thinner lines that connect the 2 points represent the average differences across reviewers, or the individual differences across reviewers. I can color code both those pieces of information. So yellow horizontal lines represent the female intercepts. The green horizontal lines represent the male's intercepts. And the same deal with these connected points. So the ones that are yellow are female, the ones that are green are male. I can use those 2 pieces of information to draw 2 separate prediction lines, one of which uses the female intercept and the female slope, and the other of which uses the male intercept and the male slope. Let me ask a question here. So I've got 2 lines that are not parallel to each other. When we worked with graphs in the past, what does it mean to have 2 lines that are not parallel? It's an interaction, yeah. What I've done in a little bit of a more complicated way than we've seen before is I've allowed quality to interact with participant sets. Something else that I get from this model is the average sex effect. So what's the average rating for males versus females? And does it differ from males versus females? So let's think for a second about how to modify this formula syntax in Elmer. I talked about how there are sort of two stages to fitting a model in Elmer. There's the first stage where you get these individual intercepts and slopes. And then there's the second stage where you're looking at the averages across those intercepts and slopes. So first things first, I'm adding a variable for participant sex. Do you think that goes in this section of the formula or this section of the formula?
Second stage.
First section. Right there.
The green one? Yeah, that's that where I'm calculating those grand averages. So I talked about how participant sex, it doesn't vary within participants, so it can't contribute to this first stage. But it can contribute to that second stage. So the way I modify this formula is I add an extra space for participant sex. And I'm adding a star that says I want both the effect of sex, the difference between males and females, and I want the interaction between sex and volume. That's what I showed you on that previous graph. So what we've done here is we've taken something that does not vary within participants. It's a fixed characteristic of participants. We've allowed it to interact with something that does vary within participants. All right, let's see if we can tie some of these quantities to what we see on the graph. So how about this first row? This is the intercept. How do you think the intercept is represented on this graph?
I think it's where the dashed line crosses the black line.
Yep, we've got this dashed line right here. That's halfway between high and low quality. This black line represents the average quality difference for males versus females. And where the dashed line meets the black line, that's that intercept. And if you were to use that intercept in a sentence to say something about rate reviews, well, what does that intercept tell you about rate reviews?
Rating grant reviews across both high, low quality, and males and females.
Yeah. The average score given to the grants across males and females in high and low quality grants is 2.88. One thing I want you to notice here is that the interpretation of this intercept is very similar to the interpretation that we gave when we worked with, well, basically any other model. It's the predicted value at 0 in all of our predictors. 0 in this case is halfway between males and females, and halfway between high and low quality grants. Up this next row, the coefficient for quality dichotomous.
Is it the predicted difference in one reviewer's rating of high quality and low quality grants, average to normal sex?
Perfect. This is the average difference in the ratings given to high and low quality grants, average averaged across the swing sets. Notice again that interpretation is very, very similar to the interpretation of other similar coefficients that we've seen in other kinds of models. When I didn't ask this, but this is the place that we find this on this graph is it's the slope of this platform. So quality is on the x-axis. The black line represents the average across males and females. This is that slope. How about this next row? So this one says
The difference in the scores between participant sets when high and low quality are average.
absolutely. So this represents the difference between male and female reviewers and the average scores that we gave to their grades, averaged across all. Again, the interpretation is really, really similar to other models that we work with. And how might that coefficient be represented on this graph? Yeah.
I'm not sure, but is it the difference between the green line and the yellow line at the dash line?
Absolutely. So when we've worked with these kinds of models before, that coefficient has been the difference between these two lines. So it's that vertical distance. What about this last row? So first of all, how might you use that coefficient in this list?
The difference between low quality and high quality grant scores that reviewers give decreases by 0.73 when you go from males to females.
Perfect, absolutely. So this is a difference of differences. It tells you how does the difference in that quality difference vary for males versus females, or alternatively, it tells you how does the gender difference change when you're looking at low quality grades versus high quality grades. Just like when we've worked with interactions before, this tells you how one coefficient changes across all the system. And how would that coefficient be represented on this graph? Yep, it's the difference in slopes between the yellow line and the green line. Or if you prefer, it's this vertical distance right here, here, minus this vertical distance here. So at the start of the lecture, I mentioned how you can also think about fitting these models in terms of what you're doing to a transformed Y data set. So let's see what that looks like. So what I'm going to do is use spread once again to take quality and give separate columns for low versus high quality grades. So I'm taking that information that used to be stored in a column and spreading it across multiple columns, resulting in a shorter data set with 50 rows instead of 100 rows. This data set ought to look fairly similar to the one that we looked at when we didn't have discrete sets. All that we've done is we've added an extra column for discrete sets. So let me ask you here, how might you take this data set to get a model corresponding to the average scores across low high-quality grades? What might you do? So what I want this model to tell me is how does the average score that the reviewers gave to high and low quality grades vary across for male versus female reviewers?
Is that the sex variable, like the sex coefficient?
Yeah, so I'm working with this sex column right here. But what do I need to do first in order to fit this model? I have to create some sort of derived one.
Just average negative 0.5 and 0.4.
Yeah, so you take the average of these two columns, take the average of these two numbers, these two numbers, these two numbers, these two numbers, and these two numbers. And then what would you do with that average?
Just the average for males, and we have the average for females.
Yeah, you just fit a model with this one sex and intersex.
And in the output, it is the interpretation of the sex coefficient, right?
That's correct. Yeah, it's a little bit different in that you have to actually fit two linear models instead of just one. That has to do with the fact that each of those linear models has its own error. So one of the models that you fit, it has to do with this average column that we create. And we can also fit the second model where we take the difference between these two numbers and fit a 2-parameter model instead of a 1-parameter model. So we're going through a very similar process as when we didn't have discrete sex. The only difference is instead of looking at two intercept-only models, we're looking at two 2-parameter models that have both an intercept and a coefficient for sex. So if you want to remember why this is the case, think back to the fact that this is a 2-stage process. You get your derived quantities. You can think of them as either coming from these little miniature linear models, one per participant, or you can think about calculating these averages and differences in the Y data set. And then you fit a second model, an overall model, on each of those derived quantities. So this was a conceptually heavy lecture. We're going to be going through these concepts again in later lectures. But a lot of the seeds of what we went through today are in Monday's lecture, where I talked about doing these little miniature linear models and then doing the second stage. Giving you a bit more of that framework for understanding how the guts of this process works. So just to recap, you can think of analyzing repeated measures data as proceeding in separate stages. In the first stage, you get those, I'm calling them within unit quantities of interest. Within unit just means within reviewer or within company, within school, within classroom. You break apart the data set into as many sub-data sets as you have units, as you have disciplines or schools or whatever. Then you calculate some quantities on those separate data sets. And then in the second stage, you conduct an overall analysis on those quantities that you derived. this will not be true for the more complex models that we consider, but at this early stage, you can think of that process of fitting those little miniature linear models as being equivalent to taking some averages and differences. And in fact, I personally like to work with averages and differences sometimes because sometimes it's easier to talk about, sometimes it's a little more to. You will see averages and differences and the analysis of those in papers, so it's just to know that there's this some. If you're making your model a little bit more complicated, one of the things that you have to think about is whether the extra variables that you're adding to your model vary within unit or do not vary within unit. We haven't considered what it looks like when your variables vary within unit. I'll show you that on Monday. But when they vary between units, those variables go in that second stage of analysis. And that's it. So on Monday, I'll show you a bit more of how to add other kinds of models to your, other kinds of variables to your model. You'll get to use Elmer a bit in this next lab, although it's, we won't have everything that we covered this week, taking it slow in the stages. Have a good weekend, and I'll see you next week.